Hi guys, this is rotational motion video 2. So I want to point something interesting about this picture here. Now, so I've got 3 circles about the same axis. There's 1, 2, 3. So if I look at the, let's say the angle here, okay, I know it's small, but there's the angle right here. If I notice that a radius 1 has an S1 that's very small, and as the radius increases, the S, or swept area, increases. Notice that? As the area, the swept distance here increases as the radius increases. Okay, so that's something very important to look at as we get to some further examples of torque. So it says, basically all points on a rotating rigid disc move through the same angle but different arc lengths. So the angle is the same, but the S is different. Okay, so S is different, and then the radii is different. Okay, so the S and the radii are different, and the angle is nothing more than a proportion between these two. So here's an application then. So if I've got angle, we know the angle is equal to the swept area over the radius. I can rearrange that and say that the swept area is equal to the radius times the angle. Okay, so this is something that's called angular displacement. Okay, S is the displacement, the angular displacement here. So this will give you some tools to be able to solve for that. Okay, as you're going to guess, there's also other angular quantities. Okay, there are other angular quantities. One being, we'll actually write it like this. This is angular velocity. Okay, angular velocity. And this can be defined as the change in angle over the change in time. Now, so this is different than our velocity, because originally our linear velocity, just as a side note, was change in displacement over change in time. So this is a bit different. Our angular velocity is in relationship to the angles. So angle over time. Okay, take a second to write that down. And the other quantity would also be something called, I always had trouble drawing that. It's an A, but it's like a, I'll have to fix that for you. Okay, we'll call this angular acceleration. Okay, and that's written as the velocity, our velocity here, over the time. So this is our velocity over time, or linearly it was this, the change in velocity over the change in time. But now it's just the velocity angular over the time. Okay, so there's some tools for your toolbox. I'll make those a little larger so you can see those. Put a box around them. So now that you've got these formulas, I'm going to give you the linear relationships. Okay, so here they are. Okay, linear velocity is equivalent to the radius multiplied by the angular velocity. So if we want to find the linear, okay, this is to go to linear. Okay, and then we can do velocity is equal to, linear velocity is equal to the radius times the angular velocity. And then also for acceleration, okay, okay, this is our linear acceleration equals the radius times the angular acceleration. Okay, I'm just going to point out that this is angular, and there's the little difference is that little line that you put there. This is linear. Okay, so you have these two formulas to convert back and forth from linear to angular. And you see how it actually depends on the radius. Okay, it all depends on that radius. Okay, so the bigger the radius, the bigger the linear acceleration. The bigger the radius, the bigger the linear velocity. So I'll let you guys copy down those formulas, and we'll give you some work to go along with that.